So it's a pleasure to welcome Leonardo Cavenaghi of University of Campinas, speaking on the complete dynamics description of positively curved metrics in the Wallach flag manifold.
Sorry.
Other homogeneous spaces.
Yeah, I would like to thank you very much, Caroline, for the kind introduction, as well as to Emilio, who was very happy to be contacted to give you this talk. I must say that I'm a little bit out of shape about giving some online talks, especially on this Beamer style, because I usually make like some writing, even online, but since there are amazing pictures here, at least on my beliefs, I'll chose to make this Beamer. Okay, so this is the work is about the dynamics description of positively curved matrix, of course, in the Wallach flag manifold, but also on some other homogeneous space. And I think that I shouldn't like tell you, especially in the seminar, why homogeneous spaces matter, but I would like to put some effort about trying to make you understand what homogeneous space are really important to me, and because especially because of the kind of work that I am doing. And I must say this is work in collaboration with Lino Grama, and that's my supervisor since I am a postdoc at the University of Campinas, Ricardo Miranda Martins, that is also a professor at the University of Campinas, and Douglas Novaes, that is also a professor at the University of Campinas. Being these last two, Ricardo and Douglas, people that work with dynamical systems. So as you're gonna see, there are a lot of dynamical systems here in this talk, okay? But of course, I'm not touching that in a very deep level, but and at least as I understood from my co-authors, there is nothing as some really difficult about the dynamical system part on this work. That makes something special about this kind of approach to this kind of problem, okay? So let me just give you some like some guide tour about what I'm going to talk in this lecture. So I will start with a bit of folklore that you understand what I do mean by folklore. And then this work is very related with different notions of intermediate curvatures that has been a massive topic, bringing the attention of a lot of experts. And I'm no expert on this kind of stuff, but I'm trying to figure out something related to this. And this is more or less the spirit of the whole thing. I'm going to try to present my results in collaboration with my co-authors, but also trying to make you understand why did I got interested on this kind of problems, okay? So let us begin with this kind of a bit of folklore that I just mentioned. And one disclaimer is that I use this citation here using BibTeX just because at the end I will put the bibliography at display, so don't worry, I will cite properly the names of people that I'm citing just to making some remark here. So there is this seminal work of Bonn and Wilken where they prove a sort of converse to the classical Bonn-Meyer's theorem in Riemannian geometry, showing indeed that non-negatively curved, simply connected manifolds admit matrices with positive Ricci curvature. This is done by the means of studying Ricci flow of Riemannian matrices on this space. A byproduct of their results is that when you look to this homogeneous space here, this SP3 over this SP1 times SP1 times SP1, they can ensure the existence of a matrix with positive sectional curvature that under the homogeneous heat flow that I'm going to recall to you very soon, loses this property of being positively curved. It means that there exists a plane that is non-positively curved. So what is the idea about the construction of this metric to begin with? The point is that some homogeneous space can be can have their geometry better described when looked from the point of view of total space of certain bundles. For instance, this particular one that is of a dimension 12, it can be described as a fiber bundle with a fiber being a sphere, the S for sphere. And then you have the very special metric there and that is an Einstein metric on this space. And by the very classical procedure of the canonical variation, where you shrink the fibers of the submersion by this parameter t here, then you can get a metric with positive sectional curvature. More importantly, when you reparameterize the whole metric, not only shrinking the fibers, you can show that this metric is a solution to the homogeneous heat flow. And I see that there is there is a typo here. This G2 should not be G2, is GE, sorry. And the point is that when you have a very close neighborhood to your Einstein metric for this family of solutions to the homogeneous heat flow, you have metrics with positive sectional curvature, but such that when you look the long time behavior of these solutions, these metrics become to have directions planes with non-positive sectional curvature. Okay, so this is a consequence of the work proving this kind of reciprocal, this kind of converse to the Bohnemeyer's theorem. Okay, but then what do I mean by a folkloric aspect of this? The folkloric aspect comes from the fact that Bohn and Wilken, they remark on their paper that for the flag manifold SU3 over the torus, the maximal torus for this manifold, the same analysis from the point of view of ODEs that they employ to the 12-dimensional example cannot be straightforwardly applied. However, they argue that, well, we can promote some kind of modification on the proof in order to achieve analogous results, meaning that metrics with positive sectional curvature on this Wallach flag 6-dimensional manifold can develop mixed curvature planes under the homogeneous heat flow. Sometimes later, because this paper of Bohn and Wilken, if I'm not mistaken, is like 2007, then Zhang and Wallach, they aim to via different, they were also working with different aspects of homogeneous heat flows for some flag manifolds, and they proved this assertion of Bohn and Wilken, but later Abiev and Nikonov, with aiming different results as well, recovered the statement, but also promoted some improvement to it. To be more precise, Zhang and Wallach, they proved that there exists a metric with positive sectional curvature in this Wallach flag manifold that is deformed to a metric with sectional curvature under the Ricci flow. More interesting, as you're gonna see, I'm gonna talk about like different notions of intermediate curvatures. The heat flow for the same metric that they shows enjoys the property that the signature of the Ricci tensor, recall that the Ricci tensor is a symmetric tensor, and indeed on the homogeneous case, we can make a very good diagonalization to it, and the signature of this Ricci tensor, it changes sign. The signature changes under the Ricci flow. So this is an answer on the direction of, well, positive Ricci curvature should not be maintained as well. And this result about due to Abiev and Nikonov shows that, well, genetically, if we start with a metric with positive sectional curvature on this Wallach manifold, it will lose this property under the Ricci flow. Okay, so as you can see, Zhang and Wallach is more related about, well, let's pick a particular metric. Although they do provide some qualitative analysis on their paper, we take this a metric and we can show that it has positive sectional curvature that loses this property. While Abiev and Nikonov result is more like genetically, we have the no maintenance of positive sectional curvature. But when you look to this kind of results in perspective, you are more or less tempted to think about, well, this kind of thing about genericity is very interesting. What can I say about the space of matrices with this kind of properties, and what can I say? What is this telling us about the dynamics of these matrices under the Ricci flow globally? And this is what I ask about: can we say better, or can we generalize the results? And a very small contribution that we made first, and this was only made with myself, Lino Grama, and Ricardo Miranda, is that we can show the existence of an invariant matrix on the SU3 over T2 manifold that has positive Ricci curvature, but that evolves into a matrix with mixed Ricci curvature under the homogeneous Ricci flow. Well, of course, this result was already obtained in some sense by Zhang and Wallach and also by Adiev and Nikonov. But the point here is that we construct the matrix with Ricci curvature, not relying on the positivity of the Ricci tensor. Okay, but just wait a bit, because once we made this analysis, it's natural then to ask, what about different notions of intermediate curvatures? That I'll explain to you better in a moment, but let me state here that for each d varying from 1 to 4, there exists an invariant matrix on SU3 over T2 that has this Ricci d positive. And what do I mean by this Ricci d positive in this scenario? For now, I'm just saying that, well, if I say that I have H1 positive, it means that I have positive sectional curvature, okay? And then if I had took like d equals to 5, that is the dimension of the manifold minus 1, then this Ricci d equals to 5 would be the Ricci curvature of the manifold. So here I'm varying strictly between positive sectional curvature that I'm including, but not including positive Ricci curvature necessarily, because, well, the first result tells us that we do know what happens about positive Ricci curvature. So let's understand what happens in this range between sectional curvature and positive Ricci curvature. And the point is that for each d that can be 1, 2, or 3, like positive sectional, or this kind of curvature that I will explain to you that has d equals to 2, equals to 3, we can show the existence of matrices with this curvature, positive curvature properties, but that do involve two matrices that lose this property under the homogeneous heat flow. More particularly, I can find a vector such that the Ricci d of this vector is non-positive, and I will give precise definitions to it very soon. Okay, so let us begin. And why did we get interested about proving this kind of results? And this has more or less this came from because we went to a conference in Cordoba where I met Emilio, and then there are people working with amazing stuff, and then suddenly we faced this work of David Gonzalez Alvaro and Massume Zadi that I found it quite interesting, and I never had thought about looking to positive intermediate curvatures in my life. But the way that they wrote this paper really made me to, well, let's sit and see what kind of things that you can do. And fortunately, I had the correct people to discuss with. That was Lino and Ricardo at that time, and Douglas comes later. But let's see what we do have. But I should mention that the work of David Gonzalez Alvaro and Massume Zari, they studied some flag manifolds, okay, that are generalized Wallach space. So they do not approach this kind of this 6-dimensional homogeneous space here. And based on some results of Lawrence Moye and Miguel Vasquez and David, they studied the existence of matrices with positive intermediate Ricci curvature on this kind of Wallach homogeneous space, and then show that the curvature properties are not maintained. Among other things, very general results under the Ricci flow. Okay, so let me explain. Yes, Emilio, of course.
Can I ask you something now?
Yeah, of course.
Why are flag manifolds special for this kind of results? Because so far I have seen only flag manifolds, right?
Yes, and we are only approaching this. I'm just give you some hint about the Bohn's-Wilken work, and then I will say to you why I care only about flag manifolds.
But why do you do it, or for something general that everybody?
Yeah, as I understand, here's the thing. On this work of David Gonzalez Alvaro and Matsume, of course, I think that Matsume is here. If she can correct me if I'm wrong, but they rely very much on this Bohn's-Wilken work. And for their work, they use a very special kind of decomposition of the matrix on flag manifolds by these isotropy summands. So you have nicely formula for the computations. Also on the paper of David Gonzalez, Miguel Vasquez, and Lawrence, they show, they promote a very theoretic setup to verify the existence of matrices with positive intermediate curvatures, especially on flag manifolds, especially using normal homogeneous matrix. And then they make the analysis considering this kind of ODE technique that was developed by Bohm and Tilken. To us, on this paper, and as far as I know, most of the literature on some Ricci flow, not every literature, but not the whole literature, but some parts relies most on the following fact. Because we do have this decomposition on the isotropy summands that I'll make explicit, we can reduce the matrix to 2 coordinates, and so the Ricci flow shall become a ODE system on the plane. And the plane, we understand very well how to do dynamical system analysis. That's the point to us. And this is quite different from Bohm and Tilken. But as I understand, it's more like you have, for one hand, nice formulae for the curvature tensors. On the other hand, you can, from the perspective of dynamical system, to ensure better results. Is this more or less like an answer? I shall make myself more clear.
Okay, later. No, it's okay, thank you.
Yeah, but as far as I know, most of the results are made with flag manifolds. Okay.
And one more question, sorry.
Yes, of course.
What about the case of homogeneous matrix on a sphere? You fix a sphere of the dimension odd, or 4n plus 3, for instance, and you have a 4-dimensional family. Is it now this case? Has been studied?
I'm not that expert about the intermediate curvatures on these manifolds, but yes, of course, you are deforming. I think that there's something made, of course, for the Berger sphere, for instance, on dimension 3, but okay, for other spheres with homogeneous aspect, I'm not sure about the whole dynamics. I think that nobody has done it, as I am aware, about just for the sphere. I think that nobody. No, I'm not sure. I'm not sure. Yeah, but we do have like some work in development trying to deal with every kind of homogeneous space with different types, as I'll get there very soon.
Okay, sorry for the interruption.
No, don't worry, and especially looking for the generalized Wallach space. Yeah, but of course you can interrupt me all the time. But then, before to begin, I must explain to you what does this intermediate curvatures? Why is it so famous right now? Because I'm seeing a lot of very good work has been done in this area, and for me, it was always a bit strange to understand where does this bis come from. Yeah, I don't even know how to pronounce bis, but like you suppose like a B. I don't know, but yeah, of course. So I'm gonna try to explain to you why does intermediate curvatures mean to me, a guy that has been working, perhaps naively, with positive curvatures. Okay, but in order to well explain it, let me give you proper definitions about intermediate curvatures. Okay, if you fix a Riemannian manifold and you fix a point, and then you collect p+1 vectors that are orthonormal, and then you say that this quantity, Ricci d v, is precisely the sum from I equals to 1 to d of the sectional curvatures. K is the sectional curvature. So you are not that when you put d equals to the dimension of the manifold minus 1, you just have the Ricci curvature on the v direction. Okay, so this is a kind of you know, you stop the procedure before you are computing your Ricci curvature. You are really in the intermediate case. So this is the expression for Ricci d, and we shall say that a manifold has positive Ricci d curvature, that I'm saying like this intermediate positive Ricci curvature for this fixed d, okay, that ranges between 1 to the dimension of the manifold minus 1. I should have written this. D ranges from 1 to the dimension of the manifold -1. And then we say that the manifold enjoy the property of having this intermediate positive Ricci curvature if for every point and every choice of d+1 vectors or two-normal vectors, so this v1 to vd can be completed to generate an orthonormal frame, we do have Ricci dv positive, where Ricci dv is the expression on the former definition here. So like for d equals to 1, this is nothing to say that the manifold has positive sectional curvature, okay? For d equals to the dimension of the manifold -1, this is nothing but positive Ricci curvature. So we are really varying concepts from the most rigid concept of that is positive sectional curvature to the weaker, if I can say so, positive Ricci curvature. And then we are collecting all the possibilities. And observe that there is a very combinatorial aspect here. And this is another answer to your question, Emilio, because this is very combinatorial, because you have to put your hands on some I don't know, some bag with some balls and drop out, because these balls are your vectors, and then you take it, and for every possible manner that you can take it, and compute this expression for the Ricci d, and it has to be positive. Okay, so it's very combinatorial. And when you look at the perspective of Lie theory, this becomes natural when you have these isotropic decompositions, as it shall be more clear. Okay, so we have this definition, and the name of the title of this slide is a bit provocative, because there are plenty of nomenclature for this kind of notion in the literature and plenty of notation. And because there are plenty of these, we are going to introduce one more. Okay, very soon. But the point is that there is this website of Lawrence Modier, where he remarks, he collects pretty much every work that deals with intermediate notions with positive curvature. And this concept here has been called this intermediate Ricci curvature, the Ricci curvature, the dimensional partial Ricci curvature, the mean curvature. So we chose it to be this intermediate positive Ricci curvature. Okay, I think that is more or less clear. What do I mean? Like we have to pick every point and every collection of these d+1 vectors, compute the expression, and it has to be positive. Okay, but let's go back to my digression about trying to explain to you why do I think that intermediate curvature is interesting. And here's another philosophical provocation, is that the top of positive sectional curvature resembles gambling with eyes in the past. This is very philosophical, probably means nothing, but as I understand is the following. Positive sectional curvature is very difficult because we have only few examples to try to guess what general properties could we do, could we guess to make our conjectures, right? But more drastically, the manifolds have not very interesting topologies. Okay, so this is why, because it's more or less like when you look to the perspective of tossing a coin, then you have to look very, very far to try to understand perhaps what is it about positive sectional curvature that makes it so much hard. And then I understand intermediate curvature as a possible way of, let us not toss this coin that could be honest or not. Let's just put that on some place to try to see some imperfection on their structure, like the coin. You're trying to see, well, is this an honest coin or not? We make different experiments with the coin to try to decide if it is honest or not, instead of dropping and collecting possible tails or not. Okay, so some results that made me really think about it, and there is another misprint here that I just noticed, that there is this result of Guijarro and Wilhelm that says, well, take a complete Riemannian manifold that has positive Ricci d curvature that can be assumed to be bounded by the same d, and then if you can find a point P such that the conjugation radius of this point P is greater strictly than pi/2, then the universal cover of the manifold that you are looking for is n minus d, not k, of course, because there is no k, no other place, and n is the dimension of the manifold. And then it says that, well, if you do have like positive intermediate Ricci curvature for d, and there is a point that the conjugate rate can be bounded below by pi over 2, then the universal cover of this manifold is n minus d connected. In particular, if d is lesser or equal to pi over 2, the universal cover of M is homeomorphic to the sphere. So this is more or less like a guess about why don't we have so many examples? Well, because we have some kind of a rigidity, right? Because, well, it gives us a sphere. So it could be much more complicated topological examples. But by far, this is the most interesting, because I recall to you that you can introduce this concept of dual foliation. And let me recall to you that if you have a manifold with a Riemannian foliation that I'm denoting by this F here, and I'm asking that this n-dimensional complete Riemannian manifold has positive Ricci curvature, this is a result of Gummer and Wilhelm, then the dimensions of these leaves of this dual foliation are all greater or equal to n minus d plus 1. Okay, so let us recall what the dual foliation means. If you have a Riemannian foliation that's regular, I mean, regular, of course, I'm not saying singular, so it's just a Riemannian foliation. It means that every leaf has the same dimension. And we look to geodesics that are orthogonal to the leaves of this foliation. You are having like this horizontal geodesics, and the leaves of the dual foliation can roughly thought to be like the collections of points that can be joined by horizontal geodesics, like to geodesics that are orthogonal to the leaves of your foliation. And the point here is that Ricci intermediate curvature is telling us that the dimensions of the leaves are bounded from below by the quantity that we can take to be n minus d plus 1, where d is the Ricci intermediate curvature notion. And this is very important because we know by a result, the result by Bucherviuken, that positive sectional curvature, so d equals to 1, leads us that the dimension of the leaves is equal to the dimension of the manifold itself. Indeed, the dual foliation is trivial in the sense that it is the whole manifold, and 2 points on the manifold can be joined by horizontal geodesics. So this result is measuring how difficult it is to produce a matrix with positive sectional curvature, not directly approaching the problem of showing the existence of matrices with positive sectional curvature that consists of taking the d equals to 1. This condition about the whole manifold, the condition about the dual leaf, a dual leaf being the whole manifold, can be weakened, like if you have non-negative sectional curvature with positive sectional curvature in 1 point, the dual foliation is trivial as well, meaning that there's only one leaf, that is the whole manifold. And but it also holds when you have like positive vertical curvature. That's a result of Esperanza, but it doesn't really matter to us here, but it does somehow, because we are more or less tempted to conjecture the following. I think that this is true. I have some partial answers about it, but the point is that this conjecture here relies very much on Ricci intermediate curvatures. And a very famous problem on positive curvatures is that a Riemannian submersion from a positively curved manifold necessarily has a such that the base has dimension greater than the dimension of the fiber. So dimension of B should be greater than the dimension of F. Okay, this is what is known as Petersen-Wilhelm conjecture. And perhaps Ricci intermediate curvature can lead to prove the following, that from the Petersen-Wilhelm conjecture infusionality would follow. That is, if you have a Riemannian summation for a compact manifold that has positive sectional curvature and the fiber has non-zero Euler characteristics, then if the base manifold is L connected for L greater or equal to 1, then the dimension of the fiber is lesser than L. while if your base is not simply connected, the holonomy group of the Riemannian submersion should be disconnected. Okay, so this is something that why I do find like a positive intermediate curvature is very interesting, because they provide you a manner to fight the monster that's positive sectional curvature without looking directly into his eyes. Okay, so more names, more ambiguous notation, and more possible confusion is that because we have another notion of positive intermediate curvature before I state the results, because I didn't state most of the results of this work yet. But so you have a manifold that is n-dimensional, and you pick some d that is lesser or equal to the dimension of the manifold. And we shall say that the Ricci tensor of M is D positive if the sum of the D smallest eigenvalues of the Ricci tensor is positive at all points. Okay, very natural. It's D positive if we take for every point the D smallest eigenvalues of the Ricci tensor, the sum is positive. Let's make it a bit more complicated. We have an n-dimensional Riemannian manifold. We pick some D from 1 to n. And we say that the Riemannian metric on M has positive D curvature. Observe the difference, avoid the confusion. This intermediate positive Ricci curvature was that notion that we have already understood about picking D+1 vectors at each point. Now we are saying positive D curvature if we denote by lambda 1 to lambda L the distinct eigenvalues of the Ricci tensor, for every collection of non-negative integers, so we have L non-negative integers that sum D, and such that one can be 0 or cannot be 0 from this L up of numbers, but I'm constrained by that their sum is equals to D, and also each of these is lesser than the multiplicity, the algebraic multiplicity of the L as eigenvalue of the Ricci tensor. So the point is that we are taking all the possible combinations of the Ricci tensor eigenvalues for every point with different weights. Not only the sum of the smallest ones, the D smallest, but every possible combination that yields D. And if this quantity is positive, we say that we have D positive Ricci curvature, positive D curvature. Okay, so this notion, of course, it encompasses the formal definition about the D smallest eigenvalues. We are taking every possible combination of the sum of the eigenvalues of the Ricci tensor. Okay, and we shall introduce a notation here. N-dimensional manifold, if we fix D, we denote the set of all admissible Riemannian metrics that satisfies the formal definition here, this definition about the curvature by this R Ricci scalar. Because if D equals to 1, okay, this notion leads to positive Ricci curvature. D equals to the dimension of the manifold. This notion leads to scalar curvature, positive scalar curvature. So this is a huge difference from the former concept of intermediate curvature that we were looking for, because on the first case, we were dealing with intermediate curvature varying from positive sectional to positive Ricci. Now we are varying from positive Ricci to positive scalar curvature. Okay, so two different notions. Very careful. I just wrote here definition 9, but no, forget it. Is the D positivity of the first definition here on this slide is sometimes, like in some reference, not here on this talk, in some reference, it is denoted by this Ricci D that we were using from the former concept. So not here, but be careful. Okay, there's a lot of different notations on the literature. Many names, many ambiguous notation, and many confusion. Okay, so about another result that was obtained with Ricardo and Lino is that there exists an invariant metric on this Wallach space here, this flag manifold, for which the each tensor is D positive for D varying, of course, from 1 to its dimension, such that the backward homogeneous rich flow loses this property in finite time. Okay, so we have constructed like matrices with positive D intermediate curvature, sorry, for such that the rich tensor is D positive, and such that the backward homogeneous rich flow loses this property in finite time. Okay, and to begin, let's move on to now the results with Lino, Ricardo, and Douglas. Lino Grama, Ricardo Miranda, and Douglas Novaes, is that we could make a very general picture about the dynamics of intermediate.
Leonardo?
Yes, yes,
Leonardo?
of course. Yes.
What about the forward flow? Do you lose the property or?
Yes, yes. You're gonna see like a picture, but there are some metrics such that the backward homogeneous rich flow loses the property, but not the front. I'm not sure how to say it. The forward rich flow maintain the property, but the backward rich flow does not. But also there are some metrics that the vice versa occurs, and also there are some metrics that they both lose this property. We shall be able to describe everything.
Oh, okay, okay, thanks.
Oh, no problem. It's my pleasure. You're gonna see like the picture of the phase portrait complete. So this results is that the one that promotes to us all the dynamics of the thing. And here's the thing: we have the 6-dimensional manifold, and now we pick D from 1 to 5. So it means that we are picking the intermediate curvature notions varying from positive sectional to positive Ricci. That's this RD sec Ricci means. And we show that this is non-empty, so we can provide the existence of different matrices with this kind of properties. And moreover, we can pick a Riemannian metric belonging to the set that is of course non-empty, such that the projected homogeneous rich flow, and I shall explain a bit what I do mean by projected, within initial condition on this metric belongs to the set. So in short time, the rich flow does not change the intermediate curvature, but for t sufficiently small, but for some t, the metric loses the set about the set of the matrices with positive intermediate curvature. So this is the point here. We can, for every notion between positive sectional to positive Ricci curvature, construct a metric that has positive intermediate curvature such that the homogeneous Ricci flow has this property of intermediate curvature for short time, but that at some point, at some instant in the time, either forward or backward, lose the property of positivity, meaning that there is a vector such that the notion of picking d plus 1 vectors does not hold. More interesting here, for very important thing here, d is not equals to 4 here. For d equals to 1, 2, 3, 5, not 4. For d equals to 4, the flow does not change Ricci for positivity, for no metric. Okay, very important. This is very different. And d equals to 4 is not the Ricci curvature. It's one notion below Ricci curvature. But for d belonging to 4 and 5, we can find some regions that are invariant from the Ricci flow, meaning that there are some basins of attraction or traps for the flow, meaning that for d equals to 4, or 5, we can find some regions of matrix, invariant matrix, such that the homogeneous Ricci flow does not escape these regions. Okay. And the analogous result about dimensions, about the intermediate curvature notions varying from Ricci to scalar curvature now. So we have the range between 1 to 6, meaning that we are considering either positive Ricci or everything varying to positive scalar curvature. We can show the same, that there exists an invariant Riemannian metric for each of these d, such that for a very short time, the metric maintains the property of having d positive curvature, but loses this property infinite time under the Ricci flow, either forward or back forward. And there exists an open region such that for each of the former notions, like you are varying from positive reach to positive scalar, there exist some regions such that the homogeneous Ricci flow does not escape in the curvature moduli space somehow sense of the flow. Like if there are some regions such that any metric does not change this property of positive intermediate curvature under the Ricci flow. Okay, so one last result before I just going very quick to some details concerning the proofs and showing the portrait phase is that I'm very interested always on about this, how to lift intermediate positive curvature. And Philip Razor and David Race, they teach us how to construct fiber bundles with matrices of positive intermediate curvatures. And we have this very classical result of Seard and Wilhelm that I have a lot of special care about this result because it was related to my PhD thesis. But so it tells us some conditions to not fiber bundles, but manifolds with isometric actions, making it possible to lift positive Ricci curvature from the orbit space that need not to be a smooth manifold to the total space, like from you have a compact Lie group connected as well, acting effectively on a closed manifold, and we have some topological hypothesis on the principal orbit of this action, and the metric and the orbital distance metric has positive Ricci, then the total space has a metric of positive Ricci curvature. And we try to combine this Razor and Race and the Seard-Wilhelm results to prove a sort of lifting for positive intermediate curvature for bundles, such that the base manifold is the Wallach flag manifold. The hypotheses are very natural in a very precise manner. So we have a fiber bundle with SU3 as a structure group, but such that the quotient is SU3 over T2. And we assume that the principal orbit of the SU3 action on the fiber has as isotropy subgroup a maximal closed subgroup. So a principal orbit has as isotropy subgroup a maximal closed subgroup. Why did we assume this? Because we have a classification. We know a classification of the possible subgroups. And then we fix df to be varying from 1 to the dimension of the fiber -1. And we assume that F admits an SU3 invariant metric with this rich df curvature. With this kind of this is not a result of Grama, Miranda, and Silva. This is a result of Grama, Miranda, and Douglas Novaes. I'm not sure why I put this Silva here. I think I have no collaborator with Silva, so I'm sorry. So just, yeah, I was not sure what I was thinking. This result is with Douglas Novaes as well. So we have this principal orbit, and then we have the assumption that the fiber has df positive intermediate curvature. Then we can show that the total space carries a metric of positive df plus 1 curvature. Okay, so the base is SU3 over T2. We have some topological hypothesis on the action of SU3 on the fiber, and we also assume that the fiber has df positive Ricci curvature. So the total space carries a metric with df plus 1 positive curvature. But even more, it admits a curve with the solutions. But for some T star, this family loses this property of having df plus 1 positive curvature. And this is the submersion metric. And the construction of this metric, of course, we start with the Ricci flow on the basis and construct connection metrics, having the metric with our assumption on the fiber, and then glue everything, and then we make the flow begin in the base. And because we know that the base loses this property, the total space shall lose this property at some point. Okay, so I'm going to be very quick here about manufacturing examples. Why does homogeneous space matter, and how did we make our computations? It's very important to mention that our invariant Riemannian matrix in the Wallach flag manifold can be described by 3 positive parameters. Okay, hence we shall very often abuse notation to the descriptions and identify every metric by 3 parameters, x, y, and z. But everything that we are going to do about the restriction to studying the Ricci flow shall be done projecting the matrix on the tetrahedron x plus y plus z equals to 1. So we are constraining the matrix to be only depending on two parameters. You see, and that's why what we make like the projected homogeneous ridge flow, because we are seeing the homogeneous ridge flow projected on this tetrahedron. Because then the metric depends only on two parameters, and since it depends only on two parameters, then we can study dynamical systems in a better way. Okay, so this is the point. And of course, I'm going to be very quick here, but when you have like a reductive homogeneous space, and usually denote the tangent space to the origin by M, we have this bracket maintenance and everything. But the point is that we can decompose the tangent space at the origin of the horizontal space as pairwise non-equivalent subspace that are invariant by the isotropy representation at the origin on this homogeneous space. And so our matrix become diagonal somehow, because we have here these parameters x1 to xn, and b1 is the negative of the Cartan-Killing form restricted to this invariant subspace. And of course, the same happens to the Ricci tensor. So we have only numbers here, and everything becomes way more easier to describe. And this is a very important aspect about homogeneous space. It's also very important to mention that when there is the paper that from Wilhelm that I just mentioned, where he asks about, well, a good point to trying to understand the intermediate curvatures should be looking for homogeneous spaces. This is in part what we have been doing, but I must remark that Domingues Vasquez, David Gonzalez Alvaro, and Lawrence Moya provide some very interesting results about intermediate curvatures and homogeneous spaces. And also, of course, the work of David and Masume also do very well with this intermediation notions constructed, exploiting a lot this isotropy representation. But also the work of David Wraith and Philip Razor can be strengthened in this setting, in the sense that they proved the very general results to the existence of positive intermediate curvatures. But in the homogeneous setting and fiber bundles associated to it, better results are always possible. So to summarize the thing, I think I'm gonna just skip it here. But the point is that we were able to show the particular basis to the tangent space at the origin of for this Wallach flag manifold, and we made a lot of computation. We can put the tables with the sectional curvatures, the structure constants, everything, and we were able to write down the Ricci intermediate curvature notions here, just in terms of some coefficients. And the point is that the problem became very, very, very combinatorial from sectional to Ricci, and for Ricci to scalar, we just could compute this Rx, Ry, Rz. These are the eigenvalues of the Ricci tensor. And then the conditions are very, very, very combinatorial. So this is an interesting point about this homogeneous space, especially flag manifolds, because everything can become very combinatorial. And this is something that we have used. I'm just going to skip it here because I'm going to say some words about the projected homogeneous ridge flow. And of course, you may all be familiar with the homogeneous ridge flow, and there are also the normalized ridge flow that enjoys the property of not varying volume. And the point is that for making the Ricci flow for homogeneous space is very, very easier than standard Ricci flow, because every PDE is reduced to ODEs because of this parameter decomposition by the isotropy representations. So we do have like a system of ODEs. And just very important to mention that equilibrium points of the Ricci flow in the homogeneous setting for normalized Ricci flow is nothing but Einstein matrix. And it's very important to recall to you that in the work of Bonn and Wilkin, they rely some part of their analysis to matrices that are very close to Einstein matrix on the manifold. This is somehow related to what we have been doing. But the point is that the Ricci flow is an autonomous system of ordinary differential equations, where I will remember to you that xk is just the parameter that corresponds to one entry of the metric, and yk is a parameter that corresponds to the Ricci tensor, but it's very useful to transform this equation in another ODE by looking to the Ricci operator as a linear transformation. And so the ODE becomes in this manner. This is rather classical. There are a lot of references in the work of Masume and Davi. They explain everything, and also on our papers. I'm just gonna skip it because the point is that I said to you that we're the flag for our flag manifold, the isotropy, it's reduced to three parameters. We have three invariant subspace for the isotropy representation. So we have the matrix to be described by x, y, and z, and so we have three eigenvalues for the Ricci tensor, and we have the equation for the Ricci flow. But we are assuming that x plus y plus z equals to 1. So we are looking for a matrix on the tetrahedron, and so we would like to understand, can we make a globally equivalent dynamical system on the plane by looking to the face of the tetrahedron? And that's possible to do. It's always possible to restrict the analysis to this tetrahedron. And so the ODE related to the Ricci flow become a very simple system of ODEs only on two parameters in a system of ODEs on the plane. This is a result of Linograma, Ricardo Miranda, Mauro Patrão, Lucas Seco, Eloha Esperança. So a lot of people worked on this paper to make everything possible to us to make the analysis from the point of view of dynamical systems. Okay, so let me show you some phase portraits. The first one is that here is the complete description of the phase portrait of the projected Ricci flow on the face of the tetrahedron. And there are some distinguished points here. For instance, the point A corresponds to a Kähler asymmetric. And from the point of view of dynamical system, this is the saddle point. B is the normal Einstein asymmetric. It's a repeller. And we have another Kähler asymmetric. That's a saddle, and another one that's also a saddle. So we have this phase portrait here. Okay. And some lines of this flow, some lines are invariant by the flow, and that was a huge facilitation to the first work with Ricardo, because for instance, this segment from O to A consists of a solution to the flow, and on that work we indeed work explicitly with solutions of the flow, split solutions. But then when Douglas came to work with us, we were able to make the whole analysis without relying on a specific kind of solution, leading to this very beautiful phase portraits here. I will leave you a minute to look into this. So let me explain. For each D, we have a notion of positive intermediate curvature varying from sectional to Ricci curvature. So D equals to 1 corresponds to positive sectional curvature, D equals to 5 to positive Ricci curvature. The yellow region consists of matrices with positive this notion of curvature, such that lose this property under the Ricci flow. So for instance, if you look to this yellow, you see that there are some lines of the flow going forward or backward, and this indicates us which part of the flow, if the backward flow or the forward flow that leads to the non-maintenance phenomena of intermediate curvature. And observe that the checkered regions for D equals to 4 and 5 are the regions where the flow is trapped. The flow is trapped. So in the vertex of these triangles for the checkered region, we have some kind of collapsing phenomena because one of the coordinates go to 0. And on that paper that Lino, Ricardo, Lucas, Seco, Mauro Patrão, and Lohan worked, they studied this kind of collapse under the Ricci flow. So we have this checkered region where the flow is trapped, and we have this yellow region consists of every possible solution to the homogeneous Ricci flow. So every point picked there is just an invariant metric with positive intermediate curvature that loses this property under the Ricci flow, either homogeneous Ricci flow, either forward or back forward. And of course, this is the notion to Ricci, varying from Ricci to scalar curvature. So d equals to 1 is Ricci curvature, and d equals to 6, that's the dimension of the manifold, is positive scalar curvature. Again, all the yellow regions consist of matrices with positive that notion of curvature that lose this property under the flow, and the checkered regions are matrices with this property, curvature property, that are trapped by having this property indefinitely via the flow. So once we have this kind of global portrait for the flow, then we can pretty much answer everything related to this. So different from the first works with Ricardo and Lino, in this work with Douglas as well, we managed to completely determine every possible region of escaping and everything else related to this under the homogeneous Ricci flow. Because this tool are about projecting everything on the tetrahedron. It's very important. And the combinatorial aspect is, that I just described, it is very useful to try to determine these regions. For instance, these regions and these curves in red, that when the flow crosses it, then you have some the non-maintenance phenomena when the flow crosses this kind of curve. Okay, and just to mention, there is this bibliography. A lot of good people have been working on this. I sadly did not include everyone, but everyone that I cited appear here. And once more, this is the website of Laros. It has everything that you need to do to begin to play with intermediate curvatures. And I'm very thankful to your attention, and sorry to be a little bit rushing the end. Thank you very much.
Thank you for a really interesting talk.
Thank you very much.
Wonderful face portraits there.
Yeah. I'm gonna just drop it here so people can see it. Yeah. Thank you very much, Carolyn.
Are there questions?
Well, Leonardo, more or less the same question probably, but now I see that the Wallach spaces are very particular to show good pictures. But what about in when the number of isotropy reducible, when the isotropy is split in more than 3 terms, irreducible terms? What do you say?
Yeah. Oh, the thing is that from the point of view of dynamics, things get way more complicated. We are not touching this particularly because even for flag manifolds, generalized Wallach flag manifolds with 3 isotropy summands, the dynamics tends to behave very differently. So there's another family of generalized Wallach manifolds that we are working where this behavior is completely different, even with for 3 parameters. So this is not exactly a property of the decomposition being 3 parameters. There's something else hidden there that we don't really know. But from the point of view of dynamical systems, I think that is probably very, very hard to treat for many isotropy summands because as I understand from dynamical system people, all these that are not on the plane are very hard to do. You have a better results to work with and probably particular results. Even in this case in the plane, there was some intriguing aspects. For instance, there was some particular kind of fixed points that showed to be like a very different dynamics. So, but importantly enough, for flag manifolds, there are some flag manifolds with 3 isotropy summands that tend to present a very different global behavior, even for 3 summands. Okay.
Okay. Thank you.
My pleasure.
Are there other questions? If there's no other questions, thank you again for a very nice talk.
Thank you. It's my pleasure. Thank you very much. Thank you.